Hi all. So here's Professor S's take on Chapter 2, giving you the summary again. Again, I definitely suggest you look at the other PowerPoint slides and read the chapter. Chapter 2 starts to get into some actual content, some meat that we're going to use for the rest of the book. So the first topic that you come across is a scalar versus vector quantities. So scalar quantities are things that are represented just by numbers. So for instance, if somebody said the temperature is 73 degrees outside, and everybody understands what that means. There's no direction or motion associated with temperature. Vectors, on the other hand, have both a magnitude and a direction. Right? I'm traveling southwest at 35 miles per hour. Right? So that's the difference between a scalar and a vector quantity. Uh, the next big thing that we talk about is combining forces, combining vectors together. We're going to talk about position or unit vectors and dot products. So let's take a look at what we got. So here is a group problem-solving problem. So you've got these three forces acting at this point, this particle in the middle at the origin of that xy coordinate. And they want you to find the resultant force. So you're going to find resultant force, and basically the process is you're going to take and resolve the forces into their xy components, combine the x values, combine the y values together. Then you'll take that and find the magnitude and phase angle, and voila, you'll have your answer. So the author poses solutions here, and I'll let you take a look at those. These slides are on Canvas, so you can take a look at them. They're in Chapter 2 lecture area. I'm going to show you the way I would do it here in a second. So once you got them all into x and y components, you add your x components, you add your y components together, you get a resultant force. Then you take and you find the direction, the magnitude, the angle, the vector quantities for that value. And there's the answer that they got. So the way I did it and the way that I typically like to do it is, when possible, I like to find all of my angles from the positive x-axis. So you see that in this particular example, and the author went with it. They'd use the 45 degrees from the the positive y, and you got a 30 degrees from the negative y-axis for F2 and F3 respectively, and a 3, 4, 5 right triangle on F1. So if you use the method that I'm prescribing, you don't have to remember positives and negative values. Now, for this particular one, I decided, since they gave me the 3, 4, 5 right triangle, I would use that for F1. I wouldn't go and try to find, I'm not crazy like that way, I would go and try to find the angle. So I wrote out the x and y values. Right, if we go back and look, whoa, we can't go that direction. We can only go straight ahead. So you'll see that 4/5 of the force is along the x-axis and 3/5 of the force is along the y-axis. The um, x value is positive, the y value is negative. Now for F2 and F3, you'll notice that instead of taking the angles that they were given, I took them from the positive x-axis. So F2 is actually 240 degrees from the positive x-axis, and F3 is 135 degrees from the positive x-axis. Then I use my calculator to take those are written now in polar form, and to bring them into rectangular form. So component rectangular form is the same thing uh, as, just to mean the same thing. So now you'll see that I have my x and y values for each one of them. So I took and combined those together, added my x values, added my y values, and my calculator gave me this. Well, I got the 162.8 for the I direction, negative, and then negative 52.1 for then reverse that x direction and the y direction. I put those into my calculator to convert them back to polar. Right? Polar is the same thing as scalar and magnitude, and I got 545.8 at minus 107.4 degrees from my calculator. Now that is from the positive x-axis. So that means instead of going counterclockwise, you'd be going clockwise to 100 minus 170. That's essentially what that means. So I added 360 to that, and that's 252 going in counterclockwise direction. So either one of those answers would be correct. So slightly different way to do it, different way to look at it. I always like to go from the positive x-axis. So I'm going to just kind of skip through here real quick. So what we're going to need to know how to do later on is to define a direction and a force in an xy plane or an xyz plane. So the way that we do that is we find a position vector that goes from the 2 points that we're trying to find our force between. If we take then that position vector, find the magnitude of it, so we divide the vector, the position vector, by its magnitude, get a unit vector, and then we multiply that unit vector by the force to get a force and a direction vector associated with it. So here's an example, right? In this particular example, we have a point A and a point B that are in a three-dimensional plane. So we want to find a position vector from A to B. So with point A and point B defined, what we do is we take the arrow and we subtract it from the origin. So we're going to subtract the B values from the A values for X, Y, and Z, and we'll get a position vector. So you can see here they did that with just the variables given to us. XB minus XA is going to be the X value for our resultant position vector. YB minus YA is the Y value, and ZB minus ZA is the Z value. If we divided, that is a position vector. That defines a vector that goes from point A to point B. If we found the magnitude of that vector and divided each one of those X, Y, and Z components by the magnitude, we would then have a unit vector. So what do we do with that? All right. Here's a case where we have a to B, and there's a force acting along that line A to B. So with point A and point B defined, we would find a position vector. We take B, subtract from A, get our X, Y, and Z points. Then we would take the magnitude of that position vector, divide the X, Y, and Z values by that magnitude, we'd have a unit vector. Then we could take the magnitude of the force that's acting along that line, multiply it by the unit vector, and voila, we now have a force acting upon a line. It's going to become very important in future chapters, just to be able to understand the concept, and it's in section 2.8 of the book. The last concept that we talk about in this chapter is dot product. So dot product is a way for us to find a projection of one vector upon another. When we do a dot product, we've got two vectors. In this case, you can see it from the picture, A and B. When we find the dot product, we get a magnitude. So we get a scalar value out when we do a dot product on two vector values. Again, we will use this. The process to do it is covered in chapter 2. We will use this in the future to find a projection of a force on another line or another plane. So there you go. There is chapter 2 in a nutshell.